So if you can all see, it's a nice blank white screen. The theme for this conference is time, and I titled this talk, It's Been a Year, because it has been quite a year. So I'm going to talk a little bit about, well, something that does qualify as remote memory, but specifically year-old memories. And so it was kind of timely that I'm going to be discussing this at the culmination of a year that will probably stand out for us in our entire lifetimes as being one of the more salient ones. So memory researchers have concerned themselves with really long spans of time and what's different or distinct about memories as they go from being a couple of hours old to days old to years old. But I think we can also bring to bear our own experiences now. In particular, we might be starting to do things that we haven't done for a year and trying to think about things in the before times and so on, brings our own kind of, I guess, personal experiences that can we bring to bear on this. I'm going to be describing research that I did in macaques, and so I want to frame this too in that light and in that context. So when I'm talking about remote memory, the lifespan of a macaque is on the order of 25 years. So an aged macaque is going to be, say, an 18-year-old macaque. So that's certainly a shorter range than us. Most of the people right now that are listening to this probably have memories that are older than most macaques would be. So there's that. But with respect to what most remote memory research in terms of the neural basis might be involved with, a lot of it comes from rats and mice, where a year difference takes you from an adult rat to an aged rat. So certainly in that sense, I'm going to be saying remote, but what I'm going to be referring to in this case really is one of these examples of long-term experiences. The other aspect to that is that it's memory for objects and scenes. So it's going to be multiple memoranda, many different items or events that we're going to be exploring retrieval in. And so both of those things are in contrast to, if you just do a keyword search on remote memory and some neural basis, that we're talking about something that's potentially quite distinct from, say, a rat or a mouse that might get an experience in a box getting shocked, and then we look a couple days or weeks or a month later about what that looks like. The details or nuances of that is maybe something we can pick up in the panel discussion. So just to give you that kind of framework, I'll be describing some experiences that macaques had at least a year beforehand, and the neural recordings we did as they were engaged in retrieval for new items versus these at least year-old items. All right, so this is what we asked our monkeys to do. There were two trial types. The acquisition was really straightforward for them. All that is a naturalistic scene gets shown in front of them on a monitor for 2 seconds. They can look around, and then after 2 seconds, a part of that image, so an object in that scene, will appear to sort of blink. So it'll get cued in a way that as they're looking around on the scene, they can see, oh, something's dynamic. Their job is to stare at it, and then they get juiced reinforcement. So it's pretty straightforward for them. It's just cueing that target. Now, those are the acquisition trials. All they have to do is stare at that changing item, and they'll get their reward. Then what we do is we'll bring those objects and scenes back, and those will be the recall trials. And in the recall trials, it's actually structured fairly similarly, but now they have 7 seconds of search, and it's no longer free search. That is to say, their reward is now contingent on them fixating that item, and it's not cued. So they basically have to remember the specific item in scene and stare at it to indicate that they remember that's the target item, and then and only then do they get their juice. And so those are the two different trial types, and we will go through, we did a number of items for the two animals that we ran in this test to kind of titrate to their performance levels. But they would be seeing dozens of images every day in this way. There were 3 different trial types. So a given scene that would be presented was either one that was shown in its acquisition phase for the first time. So during acquisition, it was a truly novel item and scene for that animal that day. Or during that acquisition trial, in fact, they'd actually seen that image. They'd been exposed to it anywhere from 10 to 20 times, at least a year beforehand. I'm going to talk a little bit about how that came to be, but the point is that these would then be year-old, at least year-old memories at the time they were, provided as acquisition. And then the third type were highly familiar. Those are the same images that were shown sort of day after day. Even in the past, they were ones that we kept as just very frequently repeated. And based on their behaviors, which were basically at ceiling, we called them highly familiar. This partly helps to keep them motivated, but it also gives us a check on that their performance, that if they do remember, then they behave accordingly. And so then we planted the animals with flexible linear probes, and we recorded from a number of different sites. I'm going to be describing the responses we saw from retrosplenial cortex and from the hippocampus. And so these are the probes that were an earlier version to what BlackRock now sells as microflex probes. We recorded with the DigiLink system at 32 kilohertz. So their task performance and what got us into this was what we saw with these acquisition trials. In fact, before setting this up as a formal study, what happened is one of the animals had been on break. And when we brought the animal back, we could see that she was doing well. My dutiful technician spotted that she was actually getting the trials far too quickly in a way that suggests she remembered. And I said, well, stop, don't show any more images. Let's not go through all of them. Let's actually set this up and see if it's for real. So you can see two examples. Both of the animals we tested showed this, that at least for a subset of these, even on the acquisition trials, sometimes their scan path, man, they were going quite directly to the target item in a way that you wouldn't predict from any kind of salience of that item. Not surprisingly, in terms of behavior, the performance, the hit rate here is going to be really high. That's because acquisition trials are quite simple. It's just, track the changing item, and they do eye tracker calibration this way every day. So that's not too surprising. What was interesting then was on the recall trials, that there was a difference in their performance as a function of which trial type. So these recent trials that they had seen as acquisition trials for the first time, their hit rate was much lower than when they were shown the items that they had seen a year beforehand. And so you're seeing that over on the right, that the hit rate's much higher. So this is showing some form of savings in addition to the saccade performance that you're seeing above. So we had this behavioral indication that our suspicions were correct from Patricia's earlier observations. And so then we sectioned off the neuronal activity according to trial type. And we looked at time. In this case, you're seeing example trial starting from scene onset during one of the recall trials. And what you can see is we got a really striking activity. I won't say this is the first we've seen it. I'll come back to that at the end. But a real striking, nice, gorgeous oscillation. I say gorgeous because we don't always get that in the macaque or in the human recordings that I've done in the hippocampus. It's quite a different experience from what you get when you run recordings in rat hippocampus. So in this example, you can see that we could identify this oscillation, take the envelope, and we'll do our analysis on this particular frequency. The frequency band itself is between 10 and 15 hertz. And you can see in both animals over on the right that the power is much stronger in the retrosplenial cortex than the hippocampus, but it is also one of the dominant frequencies we see in the hippocampus, not say an 8 hertz theta during this exploration. And that's not uncommon in all the animals we've recorded from so far, whether they're walking around or not. That 8 hertz is something that you see more during inactivity, especially in the lower frequency ranges. So think 10 to 15 hertz. We're calling it sigma for now. You can call it alpha, give it whatever name you like, but this is the frequency band where things are happening. And so then we divided out the trials into remote and recent. So here on the left, you can see again for both of the animals, Ellie and Ripley, if we take the envelope and then look at the power spectral density, where remote trials is going to be shown in orange and the recent trials in blue, that there was greater power during retrieval on remote trials. And this is aligned to the end of the trial. And if we look at the spectrotemporal time result plots, you can see that it is a fairly narrow band activity for both animals. And what you're looking at, the top row is the remote trials and the bottom row are the recent trials. So these year-old memories are consistently, and you can see the difference, significance map below that. That in both animals, there was a significant bump in this oscillation as a function of it being the remote memory class versus the recent memory class. And on the right, I did the same thing with the hippocampus, but you're not going to see the significance map because nothing was significant. So although you saw from the FFT plots that the hippocampus does show a little bit of power in this oscillation or in this frequency band, that there didn't seem to be a difference as a function of the category of memory. And so the next thing that we asked was, looking between the retrosplenial cortex and the hippocampus, was there potentially something that would indicate a synchrony or greater coordination between those areas as a function of whether it was a new memory or newly formed versus engaging in remote memory retrieval? And so to measure this, we looked at the WPLI, so the phase locking. First, we did it just as a function of the task and frequency band. So epochs in the task included search, ITI, and rest. And the only place where we were getting any substantial engagement between these two areas was during search. So during ITI, and when I say our rest epochs are simply these chunks of time, blocks of about 10 minutes minimum before the session or at the end of the session. And the animals usually dozed off a little bit during that time. And so again, in general, we are seeing phase locking across a range of frequency bands between the retrosplenial cortex and the hippocampus during search. We then divided up our trials and asked, is the WPLI, is this phase locking greater or weaker when we compare the recent to remote trials? So by subtracting recent from remote, anything you're seeing in the positive is telling you that the phase locking in that frequency is greater for recently learned trials than for remote trials. And so for that, we saw greater synchrony in a gamma, in a kind of low gamma frequency band. The results are separated out by animal. So you're seeing the one monkey's results on top and the other one on bottom. So now we get a switch, right? We had looked before specifically at this oscillatory bout, which is pretty clearly the strongest oscillation that was happening in retrosplenial cortex. If we drill down and say, when we're seeing this activity that seems to be stronger for remote trials, but that's happening during search, is there a difference in how the signal synchronizes with the hippocampus? And the answer is yes. Here things kind of flip. It's that recent trials are showing greater synchrony between those two areas, and that's happening in a gamma range frequency band. And so then the last thing we did said, okay, well, if we're looking at retrosplenial cortex compared to the hippocampus for these remote trials, there's something happening that seems to be greater, either engaging more circuits or engaging them more consistently in this condition. What does that mean for search in this task? What does it mean for the act of retrieving? Now, we didn't have any recordings in oculomotor areas to say, well, how is it actually directing the eyes? But that's basically what needs to happen. To get correct performance, it means they need to commandeer the oculomotor signal, not follow a saliency map, hijack whatever bottom-up processes there might be to direct the eyes to the remembered target. And so what we did to address that is we looked at the local field potential responses that are locked to fixation. So here you can see an example of the LFP itself. We knew from previous studies in the hippocampus that the hippocampus shows a phase alignment, a phase locking to the saccadic eye movement. And so we basically asked the retrosplenial cortex, and this is what we found. So if we look in retrosplenial cortex, which is in the top row, at both animals shown on the left and right, you can see the LFP traces on top, and then you can see the phase concentration on the bottom. And this is locked to the time of fixation. We've separated this out. This is for remembered trials, remote versus recent. And sorry, I'm just noticing a question, but I guess I'll gather the questions at the end. So we see on remembered trials that are remote, where we see this increase in the retrosplenial cortex oscillatory activity, we also see a greater phase locking to the eye movement. And so again, this is indirect, but I think it goes towards the idea that this retrieval signal may be engaging with the eye movement system that needs to actually manifest that memory. And that is a process that's stronger, specifically on remembered trials. It's stronger for the remote than for the recent as well. A take home from this can be, oh, great, register 10 to 15 hertz, retrosplenial cortex doing something in the macaque. But I think what I'd like to add on, or kind of how I'd like you to think of this, or how we are thinking about this, is not that the oscillation is a causal agent itself. It's picking up on a state that will be an important state to look at the underlying mechanisms, the underlying signal that may be conveyed through this 10 to 15 hertz frequency. And I don't say that this is something unique to remote memories. I don't say it's something unique to memory retrieval, just that that's a state that can be used in the system. And so to drill that down, or to try to highlight that point, we weren't surprised when we saw the 10 to 15 hertz by the time we were doing these recordings. These same animals we had recorded wirelessly. And when we did that, we saw that actually this is a kind of common oscillation to come up as they were getting engaged in various different activities. So where we're going now, and maybe some of this we can pick up on in the discussion section, but what we're doing in the lab at Vanderbilt now is we've built this treehouse. And in this treehouse, we want to be able to do world building in macaques. So we have control over 8 different touchscreens. We can do augmented reality style experiments by tracking their position and their performance on these screens, giving them different items and locations. And in this way, we hope to be able to build up remote memories like what we described before, but in an even more enriched setting. And we know that the retrosplenial cortex should have head direction cells and other kinds of signals that will allow us to decode that activity. So I'll show you right now, just as a starter, an example where the animal is now doing the objects in context, where context can be defined as rules in these habitats by corner. And so what constitutes the correct object in this case, as they're displayed on the screen, is going to depend on the screen or the sequence in which the animals are performing this task. So we're recording with linear array electrodes in the retrosplenial cortex and hippocampus. And if this is interesting to you and you're interested in doing a postdoc, we've got openings. But what I wanted to show of what we've seen, and the reason we're doing this in the treehouse now, is the following. If I go up to here, you'll see. I just wanted to give you an idea. Here's a sleeping monkey, gives us great theta. And if we get to the end, you'll see here. Oh, did it just stop? I didn't mean to stop it. This is the last thing for you. Yes. So I just want to give you an idea for those of you physiologists out there that you know, there it is. That's what we're talking about. The green trace is the retrosplenial, anterior and posterior hippocampus. Actually, anterior hippocampus and the hippocampus in pararenal cortex are the other traces. Just to give you an idea, it's not that as the animal's walking around, shuttling back and forth for reward, it's the theta that we're seeing, it's rather this oscillation.